Hey guys, and welcome back to another video. In this video, we will discuss 1.8 rational functions. Alright, so let's get right into it. So to begin with, let's define what a rational function is. So let's suppose we have some rational function r of x, and a rational function is basically just like a ratio of polynomial functions. So this r of x is equal to f of x over g of x, where f of x and g of x are both polynomial functions. Okay? Alright, so now let's do like a more concrete example. So let's say we had x minus 1 squared over x minus 1 times x plus 2, let's just say, right? So there are some key features that we need to talk about for this rational function. So the first one is domain, right? So the domain of any rational function is basically all real numbers, except you have to exclude the x values that make the denominator equal to 0, right? So in this case, we just set the denominator equal to 0. So x minus 1 times x plus 2 equals 0. And then just solve for x. So you get x is equal to 1 or x is equal to negative 2. And then the domain is all numbers except for these, right? Because if x is equal to these values, then the denominator is equal to 0, and dividing by 0 is undefined. So the domain is simply just, and I'm going to erase this real quickly, just negative infinity to negative 2 union negative 2 to 1 union 1 to positive infinity, right? Alright, nice. Alright, next let's talk about the wholes. So the wholes of a rational function. So first of all, what even is a whole, right? So if we had some graph of a rational function and say it looks something like this, right? Then a whole is basically just a point where like the function is undefined, right? Just like a hole in the graph. So like at that specific s value, there's no y value because like it may be undefined. And so then the way you find the wholes is if any of the terms linear factors cancel. So for example, in this one, you can see that the x minus 1 in the top and bottom cancels. And so then once you cancel that, you're left with x minus 1 over x plus 2. And so that means that at x equals negative 1, which is where, or at x equals positive 1, which is where x minus 1 equals 0, at that x value you have a whole because that factor canceled. Okay? And then to find the actual point, like the ordered pair where the whole occurs, you have to substitute in this x value back into the simplified expression, right? Because if you substitute this back into here, then you're going to get 1 minus 1 in the bottom, which is 0, and so then you divide it by 0, which is undefined. So that's why you have to substitute this back into the simplified expression. But anyway, so you get r of 1 is equal to 1 minus 1 over 1 plus 2, which you get 0, right? Alright, so that means that the whole occurs at the point 1, 0, right? So it occurs somewhere like, so this obviously isn't the graph of this, it's just an example, but it would occur like somewhere right there. Alright, nice. Alright, next let's talk about vertical asymptotes, which I'm going to abbreviate as VA. Okay, so vertical asymptotes are basically just where the denominator is equal to 0. So graphically, it would look like a vertical line, and you wouldn't like actually draw this in on the graph, but like it's just kind of like an imaginary line there that the graph approaches. So like notice how like as x is or how y is getting more and more negative, the graph is approaching this vertical line, and how as y gets approaches positive infinity, the graph is approaching the same vertical line. Now, a very important thing about vertical asymptotes is that the graph can never cross it, right? It can approach, it can get really, really close to it, but it can never cross the vertical asymptote. But the way you find them is like you just set the denominator equal to 0, and then you just find the x value. So in this case, our vertical asymptotes are at x equals 1 and at x equals negative 2. Okay. And then we have two other types of asymptotes. We have horizontal asymptotes, which I'll call HA, and slant asymptotes, which I'll call SA. All right. So horizontal asymptotes, so the way you actually find these are you have to like check the degree of the numerator and the denominator, and then based on a couple of relationships, you can determine which one you have. So what I mean by that is like for a horizontal asymptote, let's say the degree of the numerator is m, right? So m is equal to degree of numerator. and let's say n is the degree of the denominator. All right, so if the degree of the numerator is less than or equal to the degree of the denominator, then you're going to have a horizontal asymptote. All right, and if the degree of the numerator is bigger than the degree of the denominator, then you're going to have a slant asymptote. And in our case, let's see, on the top we have x minus 1 squared, so that's going to be a second degree polynomial, right? So we have a degree 2 in the top, and then x minus 1 times x plus 2, if you expand that out, you're going to have an x squared term, and so you're going to have a degree 2 in the bottom. So according to this, it looks like we have degree 2 in the top, degree 2 in the bottom, so m is equal to n, meaning we're going to have a horizontal asymptote. So we can actually break this down into two more subcases, which is just m is strictly less than n, or m is equal to n, right? So if m is strictly less than n, meaning like if, let's say this was 1 and this was 2, then your horizontal asymptote is always going to be y equals 0, all right? But if m is equal to n, which in our case it is, you just have to take the leading coefficient of the numerator divided by the leading coefficient of the denominator, and then that is your horizontal asymptote. So I'll say leading coefficient of the top over leading coefficient of the bottom, y equals. Okay, so for us, the leading coefficient of the top, if we expand x minus 1 squared out, you'd get x squared minus 2x plus 1. And if you expand the bottom out, you get x squared minus or plus x minus 2. And notice how the leading coefficients of the top and the bottom are both 1. So 1 over 1 is equal to 1. So our horizontal asymptote is at y equals 1. And the horizontal asymptote is just like the horizontal line that the graphs approach. So in this case, it would be like, so for this example, it'd be like y equals 0, right? So like, notice how they're both approaching y equals 0 as x approaches plus or minus infinity. Now, one key thing to note is that the graph can cross the horizontal asymptote. Like not in this specific scenario, but there are some cases where the graph crosses the horizontal asymptote, and that's completely okay, right? But yeah, just keep that in mind. And so now we have a horizontal asymptote of y equals 1. If you have a horizontal asymptote, you cannot have a slant asymptote, right? Because horizontal asymptote, that meant that m has to be less than or equal to n. And a slant asymptote means m is greater than n. But m cannot be less than or equal to n or greater than n, right? So it doesn't make sense to have both. So if you have one, you can't have the other. You can only have one or the other. So in this case, we don't have a slant asymptote. All right, now let's do another example in which case we do have a slant asymptote. All right, so let's say we have some rational function r of x, and it's equal to x minus 1 times x plus 2 squared over x plus 1 times x minus 2. All right, so again, let's just see. So the domain, oh, and one more thing is like, let's say you're given a rational function that wasn't already factored. Then the first thing you'd have to do is you have to factor it, right? But for these examples are already factored, so you don't have to worry about that. But like, if you were given some rational function that wasn't factored, you would have to factor it first. Anyway, so the domain of this is, remember, we just have to exclude the values of x that make the denominator 0. So in our case, it's from negative infinity to negative 1, union negative 1 to positive 2, union 2 to infinity. Okay. And then next, we have to check for any holes. So do any of the factors cancel out? The answer is no, right? None of the factors cancel out, so therefore there are no holes. All right, next let's look at our asymptotes of vertical, horizontal, and slant. So vertical asymptote is just x equals negative 1 and x equals 2. Horizontal asymptote. All right, so the degree of the numerator is, we have a quadratic term, right, x squared times x. So our total degree is 3. And then for the denominator, total degree is 2, right? Because you have two linear factors combined together. So notice now that the degree of the top is greater than the degree of the bottom, which if you remembered, that meant that is your slant asymptote, right? Slant asymptote means that m is greater than n. So now we have figured out we have a slant asymptote, meaning we don't have a horizontal asymptote because you don't have one or the other, right? So then how do you find the slant asymptote? Well, you have to like expand out the top and the bottom, and you have to do like long division. So if we were to expand this out, you have x plus 2 squared, which is x squared plus 4x plus 4, and then times x minus 1. And then this would give us x cubed plus 4x squared plus 4, x minus x squared minus 4x minus 4. And then simplifying this, you get x cubed plus 4x squared plus 3x squared. Those cancel and you have minus 4. So you get x cubed plus 3x squared. I'm going to add a 0x term just as a placeholder because since we are doing long division. And then divide that by this, which if you extend this out, you should get x squared minus x plus minus 2. Okay, good. So now if we just do the long division, we will get x cubed minus x squared minus 2x. So 3x squared plus x squared, right? So 4x squared, and then minus becomes a plus 2x minus 4. And then we have a plus 4, we get 4x squared minus 4x minus 8, and we get some remainder, right? We get some remainder. We don't really care what the remainder is though. So because like the slant asymptote is only like the this part. So our slant asymptote in this case is y equals x plus 4. Alright. And so yeah, that's basically how you find the slant asymptote, is you just divide them out using long division or synthetic division in case this is like just like a linear term. And then you just care about like whatever's up here, right? You don't really care about the remainder. Alright, good. Alright, next let's talk about the zeros of rational functions. So let's say we have some rational function, and I'll actually just use the same one that we used in the last example, which I believe it was like x minus 1 times x plus 2 squared over x plus 1 times x minus 2. I believe that's what it was. So the zeros is like basically we're asking the question, where does r of x equal 0, right? So we could just set this whole expression equal to 0. So we get x minus 1 times x plus 2 squared over x plus 1 times x minus 2 equals 0. And now notice that the only way this thing can equal 0 is if the numerator is equal to 0, right? Because if the denominator is equal to 0, that's not going to make the whole thing 0. In fact, that's going to make this undefined, right? So that's why the only way this can equal 0 is if the top is equal to 0. So we can just kind of ignore the denominator here and just set the top equal to 0. And then from here you just solve. So set each of these factors equal to 0, and then you'd get x equals 1 and x is equal to negative 2. So these are just the zeros of this rational function. Alright. Okay, let's do one more example of finding the zeros. So let's say we have r of x is equal to x plus 1 squared over x plus 1 times x minus 3. Okay, so again, to find the zeros, we could just set this equal to 0. So x plus 1 squared over x plus 1 times x minus 3. So now you have to be very, very careful, right? Because yes, you can set the numerator is equal to 0, but first thing you have to do before that is make sure, like you have to check any values that x cannot be, right? So you have to like make sure that your x value is within the domain. So if we were to find the domain of this rational function, it would be from negative infinity to negative 1, union negative 1 to 3, union 3 to infinity, right? Meaning that if our x value that we get is outside of this domain, then that means that it's extraneous, right? We can't have that. So we will just continue as normal. We have x plus 1 squared is equal to 0, and from here we get x equals negative 1. So now we have to check, is negative 1 in our domain? And it is not, right? Because negative 1 is not included here. There's a parenthesis, so that means it's not included. So this is extraneous. So that means that this rational function actually does not have any zeros, right? So it like probably never crosses the x-axis. And that could be for a variety of reasons. And it might be like because there might be like a horizontal asymptote of y equals 0, so that's why it never crosses, or it maybe just shifted, right? But yeah, it never crosses the x-axis in this case. Okay. But yeah, other than that, that's pretty much it for rational function. That's all you really have to know. It's relatively easy. If this video helped you, definitely make sure to subscribe so you don't miss any future videos, and don't forget to hit the like button. Other than that, I'll see you guys in the next video.